Okay, thank you. It's a pleasure to give this talk. I wish I could be there in person to deliver it, and I'm looking forward to an eventual meeting and attending. I slightly changed the title of my talk. I've tried to simplify things a little bit. I wanted to discuss and introduce some of the material that Professor Miller will be talking about in his talk, which is going to be more focused on the NICER mission itself. I want to talk about some general constraints of neutron stars and how they depend on the equation of state. And for this, we need to discuss some theoretical aspects of neutron stars and general relativity. And then I'd like to discuss several properties of neutron stars that can be measured. We will be using radio observations and X-ray observations, and also new gravitational wave observations that have become available over the last few years, which is introducing an exciting new dimension into our studies. So in terms of constraints, the maximum masses of neutron stars and the idea that the speed of sound is constrained to be less than the speed of light actually has a lot to do with determining the structures of neutron stars and determining the densities that we need to explore. And then we can go into some nuclear physics and even some condensed matter physics through the unitary gas that have enlightened us about the properties of matter inside of neutron stars. And then at the end of the talk, I want to go more specifically into how the observations are controlling neutron star properties. And for this, I'll want to specifically combine NICER observations and observations of neutron star mergers through gravitational waves. And I'll finish with a brief discussion of some of the new mergers that have been found and what we hope to be able to learn in the next few years from the accumulation of more and more events. Danny Page at the University of Mexico in Mexico City created for us several years ago this very nice composite view of the structure of a neutron star. And for the purposes in this talk, I would like to emphasize the fact that there are basically 5 main regions in a neutron star that are important. The atmosphere, very thin, centimeter or so thick outer layer, is what controls the spectrum of X-rays that we would observe, because the typical kind of neutron stars that we will observe with ages less than 1 million years, or in the case of pulsars, even older, the temperatures are such that X-rays are the dominant kind of emission coming from the surface of the star. Underneath that is a slightly thicker envelope, for which we don't have a lot of evidence for its composition, but it is true that the composition of this envelope plays an important role in determining how fast controls the rate of loss of heat from the interior. It serves like a heat blanket, and if the elements are lighter elements like hydrogen or helium that dominate in the envelope, then the star will have a relatively warmer temperature than if they're denser, heavier material like iron or so. Underneath that layer, we have the crust of the neutron star, and in this region, it's composed mostly of heavy nuclei, And at higher densities, some neutrons will start to leak out of those nuclei, and there'll be spherical nuclei surrounded by a sea of neutrons, which generally will become superfluid within a few hundreds of years after the neutron star is born. The crust is indicated up here in a schematic view. Low densities, this nuclei are spherical, but as you go to higher and higher densities into the interior of the star, the nuclei become deformed into cigar-shaped features, and then you can actually even have a qualitative phase change into what we call a pasta phase. So you can have something that looks like spaghetti, noodles of dense matter surrounded by lighter neutrons. And at even higher densities, those two-dimensional spaghetti-like features can switch to one-dimensional plates. At higher densities still, it's possible that the structure could turn inside out, and we could end up with these bubbles of neutrons surrounded by dense nuclear material. And finally, as we get towards nuclear saturation density, the bubbles disappear completely, and then we have a uniform fluid of neutrons and protons, and that's the outer core of the neutron star. And what we don't know is what happens to this dense nucleonic matter as we go to even higher densities towards the inner core. And I've left a question mark here, whether or not hyperons appear. Possibly there's a transition to quark matter. So all kinds of interesting possibilities exist there, and that's what our observations are hoping to uncover, is what this dense material in the inside of neutron stars is. It could be very fascinating. It's the only place in nature where this kind of material can exist. I don't have time in this talk to talk about the superfluidity inside of neutron stars and all of the interesting phenomena that comes about from the cooling of neutron stars and the plethora of observations related to that. And I've just kind of hinted at some of the interesting things from the neutron superfluid that can be both in the crust and also in the interior. And in the interior, we have a proton superconductor. And we'll skip over that and go straight to a discussion for the main purposes of this talk, which are, how do we go from observations of the structure of a neutron star, namely measurements of their masses and radii, to uncovering the properties of dense matter itself, the so-called equation of state. And for the purposes of this talk, the equation of state is basically a relationship between the pressure of matter and the energy density of matter. And so here's a schematic view. The vertical scale here is the pressure in logarithmic units with units of MeV per cubic Fermi. And the horizontal axis is the energy density in units of the energy densities found inside of typical nuclei. So the typical unit here, epsilon sub s, is about 150 MeV per cubic Fermi. So matter inside of nuclei would be at these densities where the logarithm of the pressure is around 0. So the pressure is just a few MeV per cubic Fermi, while the energy density is on the order of 150 MeV per cubic Fermi. So I'm not sure whether I should take questions during the talk or wait till the end. Possibly if you person that raised their hand, if they'd like to ask a question now, I'm happy to address it.
Can I ask now? Since I was not there in the beginning. Okay, so let me just quickly. So I guess the TOV equation, does it get modified if the neutron star is rotating? And this just a follow-up question. Obviously, a lot of people nowadays are pursuing modified theories of gravity. So I guess does the TOV equation also get drastically modified in some of these modified theories of gravity? So maybe the second question you'll address later on, but what about the rotation? I mean,
sure. Okay, so having discussed now what we mean by equation of state, to get to the structure of the star, we use the general theory of relativity, and it's been known since the 1930s that this results in a pair of coupled first-order differential equations relating the pressure and energy density, P and epsilon, to the mass and radius of a star. Little m here is the mass inside of a particular radius r, and the surface of the star we will denote by capital R with a total mass of capital M. So these equations describe the structure in spherical symmetry, and they're very, very similar to the Newtonian equations of structure that would occur. In fact, the second equation is virtually identical to the Newtonian expression for the definition of the mass inside of a certain radius. And the second equation, which relates the pressure gradient of the star to the strength of gravity, is modified by these three additional terms: pressure term supplementing the mass, the pressure and energy density act together in this term, and in the denominator, very important term, the effects of the strengthening of gravity as you make more and more compact objects becomes apparent. In fact, it's seemingly possible that this term can actually go to zero, which means you would need an infinite pressure gradient to support the star, and that is one of the fundamental limits of structure of the stars. In fact, if you try to compress a star to sufficiently small volume, even an infinite pressure gradient would not be able to support it. So there are definite limits on compactness of a star that this equation is illustrating. Now, in answer to the question that was posed about rotation, yes, rotation does modify the structure of a star, but typically the rotation velocities that we're rotational frequencies that we're dealing with are on the order of a few hundred hertz, and as long as the rotational frequency is less than 700 or 600 hertz, the changes to the structure of the star can be measured as percents or even fractions of a percent. So that's not going to be important. And in addition, there's a question of whether or not alternate gravitational theories could modify the structure of the star. And the answer to that is basically that we have some information already from observations, and that limits the extent to which alternate theories of gravity will come into play. We have observations of neutron star mergers, and to the extent that they fit the waveform models that the general relativity produces, we already know that there are definite limits on the structure, on the changes in structure that alternate gravity could give. So I'm not going to discuss these alternate theories. There's a plethora of papers that do discuss the effects that you could have. Typically, what happens is that it's possible that the maximum mass could slightly increase, but it generally gives rise to larger radii for a given mass, and we have definite constraints on that now. So I personally don't think that alternate theories of gravity are ever going to have much effect on the structure of neutron stars. In any case, applying the theory of general relativity means that you take this pressure-energy density relation, integrate these differential equations, and if you start with the pressure at the center of a star equal to a certain value where you have a certain energy density, and then integrate to the surface where the pressure vanishes, then the total mass that you get can be found, and you get a radius of the star. So for example, if we start with a point that's at roughly the density inside of neutron stars, inside of nuclei, and integrated that out, we would find neutron stars would have radii of around 30 kilometers, and only a few tenths of a solar mass. And as we increase the central pressure, we will produce more and more mass in the star, and the radius will shrink. And further increasing the pressure will eventually lead us to what's called the maximum mass. In general relativity, there is a limit to how much compression can occur in the star, and once you sufficiently shrink the radius and sufficiently increase the mass, you can reach pressure gradients that are fairly large. And furthermore, the speed of sound in the star, the pressure becomes large enough that the speed of sound approaches the speed of light. And but for our purposes, this term in the denominator basically begins to shrink, and it becomes impossible to support more than a certain amount of mass in a star. And continued trying to add additional mass into the star will basically lead to an instability. There are no stable solutions here, and the matter becomes dynamically unstable and would collapse into a black hole in short order, a few tens of microseconds. Now, an interesting thing about this so-called mass radius curve is that we know that we observe neutron stars close to 2 solar masses, or even more. That mass is sufficiently large that this curve has to rise fairly rapidly, which means that actually for neutron stars that we have most of our observations for, around 1.5 solar masses, that as we change the mass by a few tenths of a solar mass around this mean value, the radius actually doesn't change very much. In other words, if we measured the mass of one neutron star, we have got a good estimate for the radius of all other neutron stars. There's very little dynamic range in the radii of neutron stars as we go from the lowest mass neutron stars that are believed to be possible, around 1.1 solar masses, up to close to the maximum mass. So the radii around 1.3 to 1.6 solar masses may change by a few tenths of a kilometer. The overall radius change from the smallest stars to the largest stars will be at most of 1 or 2 kilometers. So that's a very interesting result, and but it is completely explainable by the structure of these equations and the requirement that the maximum mass be relatively large. A decade ago, we believe the maximum mass was closer to 1.5 solar masses, and so the mass radius curve could be allowed to have a lot less steep slope, and the excursion in radii was not constrained very well. But this means that we may not know exactly what this radius is, but we know that all neutron stars have approximately the same radii, and that's an important result. This figure shows the accumulation of several different theories of dense matter. Each of those theories results in a mass radius curve given by these black lines. Several of these theories, this figure was produced more than a decade ago, and several of these theories produce mass radius curves that are no longer valid, that are invalidated by our observations of neutron stars with approximately 2 solar masses. We see that these curves can't reach those masses before they become dynamically unstable. So those particular theories then have to be modified or discarded, and the ones that do survive have this characteristic that the radii don't change much during in the mass radius curve for normal mass neutron stars. They're all quite vertical here, but the absolute value of the radius is uncertain. It could be as small as 10 or 11 kilometers at the lower end, or as much as 14 or 15 kilometers at the higher end. And so here's where nuclear physics and also observations have now allowed us to restrict this radius range, and the punchline is that by the end of this talk, we will see that the radii of neutron stars, from observation, seems to be in this range of possibly 10 or 11 to 12, maybe 13 kilometers. So we've been able to reduce this range by at least a factor of 2 from observations and from nuclear physics. The other thing that I wanted to illustrate in this figure, well, there are a few other things. The question about rotation is important. If we could, the fastest spinning pulsar is 716 hertz, and at such a rotational frequency, it becomes possible, depending on the compaction of the star, that mass could be thrown off the equator. So it is possible to set a rotational limit to the mass radius in the mass radius plane, such that a star spinning faster than a certain amount by centrifugal effects will throw mass off and slow the star down. So there's a maximum spin frequency, which is probably close to 1,000 hertz. The fastest pulsar we've observed so far is 716 hertz. And with that, if that was the centrifugal limit, if that was the fastest that neutron stars could spin, then it would imply that that star has a mass and radius that lie in this gray region. Because if the radius is too large, then centrifugal effects at that frequency would render such a structure to be impossible. So we see for 1.4 solar masses that limit is about 14 kilometers. So in fact, applied to this particular star, we can already see that these two equations of state, if that star was about 1.4 solar masses, would not be able to explain that star, because the implied radii would become too large. So hopefully we will observe even faster frequencies and be able to restrict this domain further from the right. And on the other hand, from the left, we have the fact that the speed of sound in stars can't exceed the speed of light. And as a result, this means that there's a limit to how small a star can be for a given mass, and that's this causality limit shown by this green region. So no mass or radius of a neutron star can penetrate into this region if causality is valid. The last thing I would mention are these orange curves, which show the fact that if we observe a star in X-rays, we typically measure a total flux of X-rays and possibly a spectrum. And if the neutron star is radiating like a black body, then Kirchhoff's laws would allow us to determine a temperature, and then from the flux and distance to the star, we can infer a radius. But because of general relativity, since the flux and temperature are both redshifted quantities, we don't measure the true radius, we measure a so-called radiation radius, or infinity, which is a redshifted radius. And so for a fixed R infinity, there's a relation between mass and radius that's illustrated by these orange curves. So many kinds of X-ray observations of stars allow us to measure this R infinity, which is a mass-radius relation in its own right. So we will talk about that a little bit later. Now, the important aspects of nuclear physics that come into play come because of the so-called nuclear symmetry energy. The picture on the right here shows the energy of matter, of nucleonic matter, as a function of density in units of the saturation density of matter, which is 1 here. Pure neutron matter has a continuously increasing energy, while symmetric matter, composed of equal numbers of neutrons and protons, what we find in a typical nucleus, we have an energy minimum here. So in fact, this is why nuclei exist with the bulk of their nucleons at the saturation density, because this maximizes the binding of nuclei. Each nucleon is bound by about 16 MeV. But this energy difference between pure neutron matter and symmetric matter is what we call the symmetry energy. Neutron matter is important because it turns out, since the total energy of matter has to be minimized with respect to the number of protons and electrons, we find, in fact, that the number of protons in matter is very small, just on the order of a few percent. So, in fact, matter in neutron stars is very, very close to pure neutron matter. The symmetry energy is a function of density. Sorry if I'm going through this a little quickly, but can generally be expanded in terms of these two key parameters, so-called symmetry energy at the saturation density, about 30 MeV. That's the difference in energies between neutron matter and symmetric matter at the saturation density. You see here it's about plus 15, minus 16. So we get 31 MeV. And L is a slope parameter. It's basically the rate of change of the symmetry energy as a function of density. And that's typically around 50 MeV. And so the pressure of matter, it turns out, near the saturation density is controlled largely by this L parameter. So this is a very important parameter in terms of determining the structure of stars, because this determines the pressure of matter around the saturation density. Now it's interesting that the conditions of the neutron star are such that the matter is very, very neutron rich, which means that we can't just take our studies of nuclei and directly extrapolate to neutron stars, because we're dealing with situations where the proton fraction is quite different. So the symmetry energy is how we extrapolate from symmetric conditions to pure neutron matter, and so these parameters play a very important role. Condensed matter physics has given us the interesting result that since there's a kind of a perfect kind of gas called the unitary gas, which is a thought experiment where you have fermions that are interacting very simple S-wave interaction with such that the scattering length is actually nearly infinite, but also has zero range. And it turns out you can make cold atom experiments and model and actually observe atoms that are acting as fermions under these conditions. And such experiments have verified that this unitary gas can be achieved in practice and has a specific energy relation. The energy of this gas per particle is basically proportional to the density to 2/3. And what's interesting is that the neutron gas inside a neutron star at around the nuclear saturation density and lower is very similar to a unitary gas, because it also has nucleons that are interacting basically via S-wave interactions at these lower densities. They have very large scattering lengths, and the range of the force is extremely small. So in fact, neutron matter is very similar to a unitary gas, and the ways that neutron matter differs from a unitary gas always make the neutron matter more repulsive. So a conjecture is that the unitary gas equation here provides an absolute minimum to the energy of matter inside of neutron stars, and more specifically, the energy of pure neutron matter. And if that's true, it means that this range of L and SV, the symmetry energy parameters, is restricted to this green region. And calculations of pure neutron matter that have been accumulating recently give rise to these regions of for S and LV determined from pure neutron matter, and we see that they're within this allowed region, which is good. On the other hand, many nuclear forces that have been used over the years, including one of mine, Lattimer Swesti, actually have parameters that were chosen for various reasons that are now found to be invalid. At least this combination of parameters is invalid, lying well outside of the range of validity determined by the unitary gas equation. So what's interesting is that this allowed region then gives us a limit. The unitary gas conjecture gives us a limit on how little the energy and pressure of matter are around the saturation density. So this is an interesting lower bound then to the pressure. Upper bounds will have to come from other nuclear experiments. For example, the masses of nuclei and the measurements of the way that the neutrons on a neutron-rich nuclei stick out compared to the protons, called the neutron skin thickness, give us different ways to limit L and SV And for example, nuclear masses give us a nice correlation between L and SV that fit within this error ellipse. And on the other hand, the measurement of the skin thickness of nuclei, like lead or tin, gives us a different relation between L and SV that will explain those experiments. And where they overlap is then a general region that nuclear physics would predict for these L and SV parameters. So although nuclear physics can't pin down the parameters exactly, they do give us this nice correlation of them. And when we combine different kinds of nuclear experiments together, we find that the validity region is basically very, very close to this overlap region where all of them can be satisfied. And that tells us that L is somewhere in the range of 40 to 60, and the SV parameter is on the order of 31, 32 MeV. So this is a very interesting result, and the fact that the L parameter can be constrained means that we can control the pressure. We understand the pressure around the saturation density a bit better. And Prakash and I discovered years ago that if you understand the pressure of matter around the saturation density, then we have a lot of information about the radii of neutron stars, simply from the point of view of nuclear physics. We found that there's a correlation between the pressure and the radius of the star. Approximately the radius times the pressure to the minus 1/4 power is a constant. And under such situations, if you look at the pressure of matter, for example, at 1.5 times the saturation density, and look at all these different equations of state, you find that this combination of radius and pressure produces a very tight correlation indicated by this blue line with this standard deviation given by the dashed lines. So it means if we measure the L parameter, we'll measure the pressure, and that determines then through this correlation approximately what the radius is to within a 10 to 20% accuracy. So that relationship is basically shown here. So the way we measure neutron star masses and radii can be summarized. Pulsar timing allows us to accurately measure masses, in some cases on the order of a 10,000th of the solar mass accuracy. Most neutron stars are observed to be between 1.2 and 1.5 solar masses. The lowest mass neutron star ever measured is 1.17, and the largest measured masses are in the order of 2 solar masses. The largest published more or less accurate measurement is around 2.1 with an accuracy of about 0.1 solar masses. Now, larger mass neutron stars have been claimed to be observed, but the uncertainties are typically several tenths of a solar mass, and so I don't include them here because of the large uncertainties. Ways of measuring radii of neutron stars, including looking at X-rays, which come from both thermal, more or less steady emitting sources, and also bursting sources. And this includes sources that are in globular clusters that have recently, through accretion, have heated up and are now cooling off. And we can measure, for example, the R infinity of these sources. Another example of sources are explosions that occur on neutron star surfaces during accretion. And there we have the interesting phenomena that the amount of accretion is limited by the Eddington limit. If you accrete too much matter in a short time, the radiation pressure will actually prevent that matter from falling on the surface. So there's an actual physical limit to how fast that matter can fall on the surface that limits the luminosity. And it turns out that is largely explained by the mass of the underlying neutron star. So we can observe not only the cooling of these stars after they've accreted and measure one combination of mass and radius, but by measuring the peak luminosities of these accreting sources, we get another estimate of the mass and radius. And so those two combinations allow us to separately determine masses and radii. And the technique that NICER uses, as Cole Miller will explain in more detail, is basically looking at hotspots on rapidly rotating neutron stars and trying to infer the masses and radii of those stars. And the latest some of the latest information we have comes from gravitational wave modeling of merging neutron stars. And for example, the recent event, GW 170817, has inferred that the radius is on the order of, in my view, of around 11 to, say, 10 to 12 kilometers, which is in slight tension with the nicer measurements, which would predict radii perhaps 1 or 1.5 kilometers larger. But again, the uncertainties in both of these experiments are on the order of 1 to 2 kilometers, so they actually overlap very nicely. They're consistent with each other, and more observations will begin to shrink these errors, and we'll actually see if a tension ensues at some point. Now, this talk isn't going to be specifically about this event, GW 170817, but it was a tremendous achievement by LIGO and Virgo to be able to observe this first neutron star merger. We got a lot of information about it. One of the most important things was measuring the total mass and the so-called chirp mass of the components, which allowed us to infer that the total mass of the two neutron stars was close to 2.7 solar masses. We were also able to measure a quantity known as the tidal deformability, and that allows us to infer the radius of stars. So I have to skip through this a little bit more quickly. To infer these quantities from the gravitational waveform, you take a model produced by general relativistic theory for what the gravitational wave radiation pattern will be from the neutron star merger. And it turns out that there are about 13 parameters in these fitting models. Fortunately, the electromagnetic observations of this event, we could actually observe in real time the cooling from the matter that was ejected from this neutron star merger, produced very heavy elements, and those heavy elements radioactively decay during their formation, and they produced visible, not visible, but well, visible and high energy radiation. That allowed us to infer the position of the star, and we're also able to infer the distance because we could observe the galaxy in which this was occurring. So knowing the sky location and distance means that 3 parameters in this fitting model are already determined, and theoretically we can show that since there's 2 neutron stars involved and they have roughly equal masses, then the extent to which tides deform the stars and change the gravitational wave signal should be correlated between the 2 stars. So that means that we can reduce the number of parameters by 1 more. Now, the way that the stars, the structure of the stars changes the gravitational wave pattern is encoded through a quantity known as the tidal deformability, which is the ratio of the induced dipole moment to the external tidal field. And basically, it's defined as a constant K2 times the radius divided by the mass to the 5th power, and this quantity K2 is actually a function of the compactness of the star. And so overall, what we find is that this constant decrease, this K2 decreases, the love number K2 decreases with compactness. So that overall, the tidal deformability is a very strong function of the ratio of the radius to the mass of the star, possibly to about the sixth power. And in a binary neutron star, we actually have a combination of the 2 deformabilities from the 2 stars that are weighted by the relative masses of the 2 stars. Q is the mass ratio. And so the total tidal deformability observed is basically a function of the 2 individual deformabilities and the masses of the stars. And this shows what happens. This is due to Jocelyn Reed, this picture, but basically the wave pattern over seconds can be observed. In fact, from this event, we observed over 10,000 orbits and 10,000 cycles in this pattern. But towards the end, the effects of tides becomes apparent that depending on whether this tidal deformability is large, purple, or blue, smaller, the inspiral will speed up because of friction due to tides. And the amount that it changes is controlled by the tidal deformability. In fact, it's directly proportional to it. So this means that we can measure the deformability by observing the speed up in the gravitational wave pattern. And since the tidal deformability is very tightly correlated with the radius of the star, it means that the radius of the star, for example, if it was 1.4 solar masses, would be proportional to the deformabilities, measured deformability, to the 1/6 power, which means even a poor measurement of deformability can give us a pretty good estimate of the radius. So to show how well we can measure gravitational wave pattern from this event, how we could observe it and infer things, this figure shows the different confidence levels for the mass ratio, the two stars, and the chert mass. So the chert mass, you see, is very, very accurately determined from this event. The mass ratio is not so well determined, but that turns out to be not so important from the point of view of the deformability. Turns out the deformabilities of the stars, the binary deformabilities, is weakly sensitive to Q. So in spite of the fact that Q is uncertain, you see that the measurements of tidal deformability don't change a lot with that. And so for this particular event, the tidal deformability can be measured. The mean value was actually about 200 or so, and the plus or minus 1 sigma plus 200 and about minus 100. And if we go to 90% confidence, we would get the numbers that LIGO basically estimated were that the tidal deformability had a maximum of 650. So this gives us then, through the previous equation, that if lambda is on the order of 600, we see that the limit to the radius of the star is around 13 kilometers. We can do a little bit better than that by actually looking at the masses and radii that are inferred, again, with the same confidence level, 68%, 1 sigma, 2 sigma, and finally 3 sigma. And you can see that the inferred radius is on the order of say 9 to 12 kilometers at the 1 sigma level, and that holds out if we as we continue to analyze. So NICER, as I said, is a way to observe the masses and radii by looking at hotspots on rotating stars. So since Professor Miller is going to talk about this in more detail, I'll skip through exactly how the masses and radii are inferred from this technique and just sort of go to the bottom line. Sorry, Cole, if I'm stealing a little thunder here, but this basically shows the masses and radii inferred then from the NICER experiment. There were two different kinds of analyses, one led by Anna Watts, published as Riley et al., and the other one led by Cole, published as Miller et al. They gave extremely similar results for the masses and radii. You can see that there's a nice correlation between mass and radius, indicating that the one well-determined aspect of this is the gravitational redshift, or the compactness of this particular star. So although the masses are uncertain to several tenths of a kilometer, and the radii to several tenths of a solar mass, and the radii uncertain to several kilometers, the ratio of masses and radii are in fact fairly well determined. And what's interesting is to compare these two measurements from gravitational waves and from NICER. And if we just assume that the masses of these stars are so similar, we can combine these experiments by basically multiplying the probability distribution functions together. And so the overall result that we get is this, and we see that the inferred radii at 1 sigma are between about 10.5 kilometers to about 13 kilometers. And our hope for the future is that future observations, of which there have been several now, from LIGO, Virgo, and 3 run, which ended about a year ago, there have been about 40 more mergers observed, some black hole mergers, a few binary neutron star mergers, and a couple of suspected black hole neutron star mergers. Unfortunately, none of these were close enough to give us a strong enough signal to give us good measurements of the radii. For example, the only one for which we have a tidal deformability measurement is GW 190425. It's not even clear that this is a binary neutron star. If so, it would be a kind of a strange one with two very large neutron stars. I think it's more likely it's a black hole neutron star system with a very small neutron star, in which case the radius would be inferred to be only limited at the upper end by 16 kilometers, which isn't, unfortunately, which isn't much help at this point. So to summarize and to finish up, the gravitational wave measurements have provided radius information and equation of state information that is more or less consistent with what we expected from nuclear theory and from other astrophysical observations. So there were no major surprises in that sense. What I didn't talk about is that this gravitational wave measurement actually could be construed to give us an upper limit of the maximum mass from the fact that we observed mass ejected from this merger and from the total mass that was inferred from the gravitational waves. Means that this star, probably this merger, did form an object that eventually, actually quickly, collapsed into a black hole. And that gave us an upper limit estimate for the maximum mass that's not too far above the two solar masses that we already knew from pulsar timing mass measurements. NICER has provided very consistent radius information, possibly a little larger than what was inferred from the gravitational wave event, but at the 1 sigma level, the results overlap, and so overall, there's a nice general consistency. We hope that future NICER measurements of different neutron stars and also gravitational wave measurements continued from different binary neutron stars will be accumulated, which will help us refine these measurements. And gravitational wave measurements are especially interesting for me because I think that we'll be looking at very, very similar systems. So we can possibly simply add the data from these different mergers in such a way that they will be directly additive, and that should help us reduce the errors quite significantly. So I think at this point I'll stop. Sorry if I went over a few minutes. Thank you.
Thank you, Jim. So we have a few questions.
All right.
So the first question is, can dynamic instabilities occurring from addition of extra mass beyond the maximum permissible mass lead to outflow solutions?
Lead to what kind of solutions?
Outflow solutions.
Okay, so as we get close to the maximum mass, and if you add more material onto the star, yes, probably oscillations would begin, but the overall collapse occurs on a dynamic basis. And I don't think the oscillations will become violent enough to actually eject material at that point. The gravity is very, very strong, and I think the entire thing will just disappear into a black hole in very, very short order.
Okay. So the next question is, does the flux reading differ in various radiation? This is from
Repeat.
YouTube.
I'm sorry, repeat that.
Flux reading differ in various radiation. So in different kind of radiations.
Okay, so most of the energy emitted is in X-rays from the surface of the star. But in the case of, for example, of the nearest observed neutron star, RxJ 1856, that's also observed in optical and ultraviolet radiation as well. So the peak of the spectrum is in the X-rays, but on the VIII tail of the pseudo blackbody radiation spectrum, it is possible to observe these stars also in optical radiation, for example, with the Hubble Space Telescope.
Okay. So the next question is, assuming the lighter object in the recent merger was a neutron star and not a black hole, it would be around 2.5 to 2.6 solar mass. So it
That's
will,
correct.
yeah, it will push the radius to be more than 12 kilometer. So if you look at the causality limit on your plot. So are these microscopic, not barotropic or parameterized equation of state that get you to that mass and radius?
Okay, so I would refer you to this figure, which is not complete, and shows some typical results from nuclear physics calculations. So here's an example. If we look at AP3 or MPA1, they can achieve masses close to 2.5 solar masses with radii 12 or 12.5 kilometers. And it's possible, however, to produce those masses with even smaller radii. I did not attempt to show in this figure what the limit is, but in fact, it is possible to achieve 2.6 solar masses with a radius that's smaller than 13 kilometers. So even if this 1904-25 event, or I'm sorry, 1908-14 event was judged to be a very heavy neutron star, 2.6, involving 2.6 solar masses. That fact itself would not be inconsistent so far with the measurements of radii that we have around, at a maximum of about 13 kilometers. I think, however, that this particular event could be so we're talking about this event up here, GW 1908-14, with a chirp mass of about 6 solar masses. I think that this 2.6 solar mass object is actually a low mass black hole, and that can be reinforced by the event 1904-25, which is measured to have a chirp mass of 1.44 solar masses. And instead of, it has two alternative explanations. It could have been two approximately 1.7 solar mass neutron stars, or I think it's more likely it was a very low mass black hole and a normal neutron star in their 1.2 to 1.3 solar mass range. So we can't be definitive about either of these sources, but in fact, both of them would be consistent with a low mass black hole. And I don't see any problem producing black holes between 2 and 3 solar masses from the stellar evolution point of view. So I know that there's some prejudice in the community that there's a mass gap between 2 solar masses and 3 or 4 solar masses, or even 5 solar masses, for which it might be difficult to form black holes. But from a stellar evolution point of view, I don't think that the theorists involved in supernova modeling would agree that this mass gap is real. I don't think they have any problem producing such low mass black holes. Okay, next.
Yeah. Next question is, for the binary neutron star system in the merger phase, is the curved space-time correction to the microscopic theory necessary?
The curved space-time correction to what?
To microscopic theory. I think into TOV is telling, I'm not sure.
The
of state, I think equation of state, they are trying to say that whether the equation of state will change or not.
Okay.
I see. So my own feeling is that the equation of state is determined by very, very local properties of matter. The interaction length of the nuclear interaction is at most, hundreds of Fermis, and on this scale, the space-time is fairly flat. It doesn't really affect the equation of state, the conditions under which the strength of gravity is not playing a role there, because it's not varying much over the length scale. So I'm not an expert in the I think the particular question whether the equation of state might be affected by being in strong gravity, but I think that everybody from Einstein forward has basically assumed that the pressure and energy density are defined locally, and their use in the TOV equation does not have to involve any additional corrections.
Right. So the next question is, I don't understand the comment that GW 190425 is more likely a neutron star BH system. For the low spin prior, the mean of mass posterior for the primary is about 1.75 solar mass, and the maximum is less than 2 solar mass. Can you please comment on this?
Yes. So this relates to a slide that I kind of that I passed over very quickly. Let me go back to it, and I'll explain my point of view. So far we've been able to measure 18 double neutron star systems in our own galaxy, and they have properties that are very interesting. On the left, we see the mass ratio of these systems as a function of the chirp mass. Some of these systems don't have a definite chirp mass because the individual masses have not been measured, but the total masses have been measured. That's 7 of them. They're illustrated in as these curves, but since the chirp mass is not very sensitive for a given total mass to the mass ratio, and since we know that the minimum mass for a neutron star is around 1 or 1.1 solar masses, there's only a small range of mass ratios that these systems could possibly have, which means that the chirp masses of these systems, even the ones with only the total mass measured, are also pretty accurately known. So you can see that the chirp masses of known systems are between roughly 1.1, 1.25 solar masses. And this particular event was unusual in that it has a chirp mass of 1.44 solar masses, which is well outside the range of the double neutron stars observed in our galaxy. Now, you could say that, well, this is not a system in our own galaxy. It could have been formed by a encounter instead of a natural evolution of a binary star, and so on. But I think that just the fact that it's so unusual compared to the binary neutron stars that we've observed in our own galaxy, that the idea that there's 2 fairly large neutron stars as opposed to, or even 1 large neutron star and 1 smaller neutron star, is less likely than the explanation that we have a low mass black hole and a neutron star. I think the prejudice against the black hole neutron star interpretation is the possibility that a very low mass black hole exists. But as long as this is greater than the maximum mass of a neutron star, which GW 170817 sort of indicates, I prefer this solution. But I think the community may be evenly split on this question, and maybe even the majority of people might prefer the binary neutron star explanation. So again, this is all the information we have, and I think it's a matter of opinion at this point. I think the fact that these 2 neutron stars are so dissimilar from the systems that we observe in our own galaxy, to me, is a more telling point. But that's just my perspective.
Okay, so at this point, we are running out of time, so we will thank Jim once more. Thank you, Jim.
Okay, well, thank you.